Hello, we are the Compact Mobile Trigger Generator team. My name is Johan Alano. Also on our team is Alan, Christian, and Alte. Um, the goal of our project was to create a mobile trigger generator that creates a high enough pulse to break down across a spark gap switch that we made. It has to be reliable enough to do so repetitively, and it needs to be galvanically isolated for safety for high voltage equipment. Our base requirements um, were a peak amplitude of 10 kilovolts, a rise time of less than 400 nanoseconds, a pulse duration of less than 2 microseconds, and a repetition rate of 50 hertz. We also aimed to have um, a enclosed device that weighed less than 25 pounds and was entirely self-reliable. For our block diagram, I will pass it off to Alte.
Our block diagram has remained mostly unchanged for this semester. As you can see, we have a switched power source going into both a voltage regulator and a DC-DC converter. From the voltage regulator, it goes to our gate driver and our optic receiver. And then from the DC-DC converter, it goes to the charge circuit, which was switched with an IGBT dual setup going into our pulse transformer, which is then sent to the spark gap. This is a schematic of the main circuit board without the supporting circuitry for the gate drivers.
For our voltage regulator, we use the LM7805, which stepped down our 12 volts from our battery to 5 volts for the logic circuit that would control the gate drivers. This behavior was verified using a very basic circuit.
DC-DC converter is the 10 to 18 volts, around 12 is what we intend to use it with, and can output up to 40 milliamps of current, and it has a good amount of isolation voltage as well. It requires a lot of supporting circuitry as shown in the diagram below, fused on both sides with a lot of filtering for the power.
For our pulse transformer, we use the Excelitas TR180B. This has a 20 kilovolt peak output, and it provided us with a 1.5 microsecond pulse width. As you can see in this image where we tested with a signal generator, we were able to get the response time that we needed.
For our fiber optic receiver circuit, we are using the Broadcom HSDR2412Z series. It's interfaced with the UCC27425 dual channel low side inverting non-inverting gate driver. This is intended to take a user signal and send it to our IGBT switches. The gate driver we have is 27525. As I said, dual channel inverting, non-inverting. This ensures that while one circuit is on, the other is off. So we can charge and then discharge, and they simultaneously switch back and forth.
Our IGBT is the Infineon IKW40N65RH5. We chose it because of its fast rise time and its capability of handling 650 volts. Tested with our gate driver, we were able to verify that it produces both the repetition rate and response time that we needed.
This is the results from our simulation. This is a simplified version of the circuit without all the supporting circuitry for like the DC-DC converter and such. It generates the correct pulse waveform we're looking for at a very high speed, and that speed is dependent essentially on what capacitor you pick. With the higher values, we can just increase that decay time on that curve, but it's still in like the nanosecond range usually, so it's fast enough for our requirements. This is our assembled PCB along with the PCB design. It's been assembled but not really confirmed working at the moment. There's a slight problem with the switching circuit. Not only that, there has been a problem from a missing trace from the fiber optic to the gate driver. That's been corrected. And the switching circuit still isn't functioning, but it is currently being worked on at the moment.
Our intended battery for this circuit would be for a 4S LiPo battery. This is because of its relative robustness, its capacity at 14.8 volts, and its price. Moving on to the high voltage spark gap switch, Christian and Alan will be speaking on that.
So this semester, one of the main topics that we kind of covered for our project was spark gap switch and learning the spark gap breakdown process. Essentially, you have two electrodes with a dielectric material in between, and whenever there's a high voltage applied to the electrodes, it would create an electric field in between the two electrodes. But once the electric field strength is exceeded and and it causes the dielectric breakdown, then the dielectric material becomes ionized and creating free electrons and ions, which essentially will create some sort of spark in between the two electrodes, kind of in a way closing the circuit. And right here we just have another image kind of showing the direction of the electrons and the ions.
Finding the voltage breakdown, we are introduced into Paschen's law, which is equation for the breakdown voltage needed to initiate a discharge or electric arc between electrodes and gas. So this is mainly based on two components, which is the pressure being used within the spark gap and the gap length. With this equation, we are able to create a Paschen curve. And with the Paschen curve, we are able to predict the voltage required to cause an electrical discharge like a spark across a gas field. And as you can see in the equation to your right, we have gas constants A and B, which are used for the type of gas that we use. For our project, we were tasked to use 3 different gases if we had time with our design, which was air, argon, and nitrogen. We also have different pressures that we wanted to accommodate with each air that would give us the voltage breakdown. And as you can see here, gas constants are based off of experimental equations. I was able to find 2 different gas constants for air based on J.D. Cobham's textbook. And these values may be used for estimating purposes for the indicated range of E and P. Compared to the previous values that I found, these gas constants seem consistent, such as air. So we wanted to substitute these values into the Paschen law. And here we have the Paschen curves that we described, where if we look towards the left side of the figure near the curve, that's where we want to predict the minimum voltage breakdown needed within the spark gap.
One malware program that we wrote to use this law to identify the gap distance for our spark gap switch. We kind of estimated a distance of 0.25 inches to 0.39 inches for a breakdown voltage of between 23 to 34 kilovolts. And then for our initial spark gap designs, this is kind of where we left off last semester, where we had the idea of using stainless steel third electrode, stainless steel fill port, and acrylic/glass base, stainless steel carrier screws for our electrodes, and then a glass ceramic cylindrical housing. And here's some images of a CAD design that we had developed last semester as our initial spark gap switch design. Beginning of the semester, we started making changes to our spark gap initial design. One of the first few things that we did was developing an acrylic base to secure the nylon thread rods and hex nuts. Our electrodes were stainless steel carrier screws, and our fill port was a brass fill port. Some of the issues with the design that we noticed was the electrodes were stationary, and we needed one of them to be adjustable in order for us to change the gap distance. The cylindrical case was glass, so attachment for the third electrode was going to be a bit of a problem. And then there was risk of gas being leaked since we didn't have the proper sealing for the spark gap switch. And so for start, some of the things that we did to solve some of those issues was first, to create the movable electrode, we would need a non-rigid flange that is conductive. This would be inside the glass container while having a precision flange nut outside the base to support the electrodes. And then stainless steel half thread rod and ball became the new electrode. So essentially, we would have the electrode being the stainless steel rod that would be able to rotate through one of the flanges that was threaded, and then the other flange that was not threaded, I don't know, was going to be where we'll be able to twist and adjust the gap distance. So here's the second design assembly where we're adding both flanges parts to our drawing. We replaced the electrodes with the new ones that we had created. We updated the depth of the acrylic base. And the fill port was exchanged to a stainless steel one that had its proper seal. Some of the issues that we saw with this assembly was that sealing holes was having sealing holes to avoid leaks. Attachment of the trigger electrode was still questionable. And then stainless steel forged pipe scope was big compared to our other parts.
So some of the updates that we saw with the issues from the previous two designs was we wanted to incorporate O-rings, which was a circular ring with a round cross section. Typically, it's made of a elastomeric material such as rubber and silicone, but we chose a oil-resistant Buna O-ring for our design. It is used to create a seal between two or more parts to prevent leakage of gases. And to apply the O-rings to our design, we must create an O-ring groove, basically a slot, allowing it to be compressed and form a tight seal. And as you can see here on the right, we wanted to add this O-ring groove into our acrylic bases so that whenever we are assembling the cylindrical case to the base, we wanted to compress the O-ring, making it a good seal. And another update for our part was that since we did see the size comparison to the previous nut that we wanted to use for the moving electrode, we decided to take the precision flange nut that we will be placing inside the casing and mill out an O-ring fitting. The O-ring fitting will be milled with a depth of 0.06 inches and will rotate around the 0.6 inches hole to secure a spot for the O-ring. And here, looking at the drawings to your right, is kind of what we wanted to send out when milling out our O-ring precision flange nut. And now going into our kind of like the final spark gap parts that we officially wanted to use is here numbered by number one being our acrylic bases, such as it has the O-ring grooves, the holes that we wanted it to provide the nylon threaded rods, and as well as placements to places to secure our precision flange nut within the acrylic base. We also have our stainless steel threaded rod with the sphere. As you can see, half of it is smoothened out for the moving electrode, but overall for the other ones that are fixed, such as our trigger electrode, they would be rigid all the way through. As for our part 3, our stainless steel fill port, that's the one that was already pre-made to secure any leakages. And for our part 4, we have our stainless steel support rod with the hex nuts, as we described, just to add more support to our design. And one of the last few parts that we have is the acrylic cylinder case that we ended up changing just because we wanted to add more depth in order to incorporate the trigger electrode. And lastly, we have the precision flange nut, where we use a total amount of 3 in our design, one being altered to having no rigids and the other just being securing the fixed electrode, as well as the moving part of the electrode. And now we come to our final spark gap final design, where we have the precision flange nuts that have been properly secured to the acrylic bases. We have our stainless steel support rods and hex nuts and set up the nylon for stronger enclosure, but we ended up changing just because of the size difference and went back to nylon and is still secured properly. We also have our trigger electrode that will be drilled through the acrylic cylinder. And one of the issues that we did have with it was the tap was old enough, so the trigger electrode did go through all the way through, but instead we were able to send out a new casing with a new tap in order to get the trigger electrode more secured. And what awaited for this final spark gap final design was the connection of circuitry, as we were going to use ring thermal connectors to the screws at the end of the precision flange nuts outside the base.
Here's just a summary of all the components that we used for SparkUp design. As we mentioned, the base was going to be comprised of a high strength UV resistant acrylic. To support beams were going to be originally high strength steel thread rods, but then we decided to switch to nylon back again. The electrical contact was going to be a stainless steel ball connected to the thread rods, all threaded rods. The gas inlet was going to be a clean and back Eurolock fitting for stainless steel tubing. The flange was a precision flange that we ordered from McMaster. O-rings, we used multiple different sizes of O-rings for different purposes within our spark gap switch. And then the enclosure was a clear cast acrylic tube. Now for the machining of the spark gap parts. So majority of the parts we were able to order, but some had to be a little bit tweaked for our purposes. So we met regularly with David McNeil from the May workshop to list some of the parts requirements, specifically on our precision flange where we need an O-ring, and also our acrylic bases and cylindrical where we need to have the sizes for our the holes for our rods, our threaded rods, both nylon and steel, and also for our O-ring grooves. However, throughout this process, there were frequent exchanges of part drawings with in annotations until we met the requirements and specifications of David McNeil. There was a lot of validating of parts and back and forth, and also receiving feedback from them, getting the best suggestions moving on within our parts. All the parts were actually built for assembly, and the work order for these parts were submitted to Dave McNeil.
So once we received all the parts from the workshop and were able to confirm to get the green light to continue, this then continued to our spark gap assembly, where each part assembly was very smooth as each part fitted in their own design designated spot. The cylindrical casing was able to expand and seal the O-ring with the new O-ring groove. And then we also used clamps from the wood workshop just to tighten up the sealing itself as we screwed on the nylon threaded rods and hex nuts. The electrodes were adjusted to the correct length for testing, and the trigger electrode was no longer loose as the new hole was tapped correctly, as we previously mentioned in the previous slides. And we added more support to avoid the trigger electrode movement by adding a hex nut at the end.
And so once we were able to finish assembly, it was time for testing. But before testing, we had our spark gaps validated and reviewed by both Nick and Dr. Wetz. And having the green light from both of them, we were able to start testing. For testing, given that we did not have our trigger generator circuit available at the moment, we utilized the trigger generator circuits that Dr. Wetz had previously developed. We made some on-site adjustments to set up the spark gap switch, circuitry for our spark gap switch, and adjusted some of the gap distances, specifically since we wanted to test only the two horizontal electrodes. Once we applied 9.7 kilovolts across both electrodes, we were able to form the arc and that we wanted for our spark gap switch. And for that purpose, we were able to see success between our two electrodes and our spark gap switch.
So now we enter our standard and codes design part of the project, where we wanted to incorporate recent codes that have been updated throughout the years, especially since we are dealing with a high voltage device. So basically, the reason we want to include codes into our project is just to reduce potential hazard. Some of the main code books or standards that we wanted to incorporate includes the NEC, which is used to protect against fires, electrical shock, electrocution, arc flash, and arc blast. And we also got standards from the NFPA 70E, which is the National Fire Protection Association, just to handle with arc flash and ground fault since we are dealing with the spark gap. We also wanted to incorporate IEC 61010 to kind of deal with the heat mitigation that may be driven to our gate drivers or any circuitry components, as well as incorporating some insulation so we don't, us as the users don't get shocked. And we wanted to space, one of the main things that we wanted to incorporate was just making sure we spaced out our low component and high component voltage devices within our circuitry or even within the spark gap. So you may be wondering, how do we know where our device fits within all those standards and codes? So from the American National Standards Institute and NFPA 70, they define medium voltage class to be greater than 1000 volts, but less than 100 kilovolts. And for our device requirements, we wanted to have a range within 10 kilovolt output within the spark gap. So for that, we wanted to define our electrical system as a medium voltage. And this includes more articles that we wanted to cover, such as the NEC Article 100, Part 2, which kind of gives the definitions for electrical installations over 1000 volts nominal. We also have Article 11.34, kind of incorporating that working space that we talked about from moving low voltage and high voltage devices apart. We also have Article 245, which is the overcurrent protection for systems rated over than 1500 volts DC, as well as Article 315.60 tables, which include the ampacities for conductors from 2001 volts to 35 kilovolts. And then lastly, we have NFPA 70B that we did talk about, but it also has a section where it recommends practice for electrical equipment maintenance. So for us, especially when dealing with the spark gap switch, if we weren't taking care of our parts, that may have altered our testing results, or just any damages to our parts would have affected any results.
For our budget, this past year, we were able to, or we had a approximate total spend of $1,038.14. It can be broken down into two main lists of parts that we had to order. Some parts specifically just for a trigger generator, and then some parts specifically for our high voltage spark gap. Right here, we kind of broke it down as to what was the cost of the parts that went into each part of the project. And coming out where our high voltage spark gap switch did consume most of the costs, and majority of that was due to reordering and ordering multiple different parts and sizes for our spark gap switch, which some of them could have been probably avoided and been redundant, but it was just another lesson that we got to learn from this project.
In terms of our schedule, our initial prototyping and implementation phase took a number of months and continued up until very recently. Our full systems testing and addressing performance was done, but we still have quite a little bit to go to validate the performance of our device. But as far as accomplishing production of both our electronic components and our spark gap switch, both of those have been accomplished. For labor, our group is mostly split into two teams. As I mentioned earlier, Alan and Christian worked on spark gap design, CAD modeling for it, and building of it, and me and Alte worked on circuit design, simulations, and electronics.
Our lessons learned, we learned that designing an assembly was a very repetitive process. And the spark gap itself, being more precise on initial drawings, would have saved time for that. We understand that high voltage requires a good understanding of standards and codes. Certain rules are there to ensure the user's safety, and we want to make that the first priority in our design always. Being cautious on our part selection to avoid unnecessary purchases. There were some parts that were bought for the spark gap that weren't really working for us, so we had to buy different ones, and we could avoid that in the future. For the charging circuit, we also learned the idea of eliminating ringing on the capacitors, so we were able to get that nice looking waveform compared to something with a lot of oscillations.
And then finally, to end our presentation, these are all the references that we use in order for my research progress. And this concludes our presentation. Thank you.